In this series of videos, we're going to be learning the details about a family of hydrocarbon molecules called the alkenes. That's right, you heard that correctly. The suffix of the word alkene is actually ene, which is different than ane. So in the same way that alkanes use their suffix to indicate that there are only carbon-to-carbon single bonds that are present, whenever you see the suffix ene in a molecule, it indicates that the hydrocarbon has at least one carbon-to-carbon double bond that is part of the molecule's parent chain, and we can take a look at a relatively simple alkane and alkene molecule here for the purpose of comparison. So first off, we'll need to make a spelling correction here. I am not listening to my own advice. We can clearly see that this is an alkane. This one in particular is butane because it has 4 carbons. Now, if we look at every atom that isn't a carbon, that being all of the hydrogens, we can see that each carbon has the maximum number of bonds that is possible for it to make, that being each carbon has 4 bonds, meaning that each carbon has the maximum number of hydrogens that is possible to be attached to a total of 4 carbons. And the word that we can use to describe alkanes is the word saturated, which is simply a word that means full of. And this is a term that is familiar to many people with a strong background in biology because the word saturated is used to describe a type of fat molecule that has the maximum number of hydrogens because of the fact that all of the carbons only contain single bonds. And fat molecules, for those with a good biology background, are essentially just very long hydrocarbon chains. The problem is that when we introduce a double bond, the maximum number of hydrogens decreases. So because each of these carbons have 2 bonds because of the double bond, that means that each carbon can only have room for 1 fewer hydrogen. So this terminal carbon on the end, in an alkane, it would have 3 hydrogens, but in an alkene, this one only has 2 hydrogens, meaning that the maximum number of hydrogens per unit of carbon is no longer possible now that we have an alkene. So the conclusion is alkenes, because of their double bond, have fewer than the maximum number of hydrogens, and therefore they are considered unsaturated because the hydrocarbon molecule contains less than the number of maximum allowable hydrogens. Now, when we represent alkenes in the form of a line structure, we can represent them like this here. So to pay attention to how many hydrogens each of the unlabeled carbons is with the double bond, all we need to do is count the number of carbon-to-carbon bonds. So this carbon here has 1, 2, 3 because of the double bond. So there is 1 invisible hydrogen here, and this one over here only has 1, 2 because the double bond isn't here. So there would be the regular 2 invisible hydrogens like this. Now, we name alkenes the same way that we name alkanes, by first counting the number of carbons in the parent chain. Since neither of these have any side chains, we would just begin with bute. And then instead of calling this butane, because there is a double bond here, we're going to call this butene. Now you'll notice that there's a space here, and we'll talk about why that is after we try naming this one. Well, this one also has 1, 2, 3, 4 carbons, so its carbon prefix would be bute, and we see that there's at least 1 double bond, so we can't call this butane, we have to call it butene as well. Now, are these 2 butenes the same molecule? Well, if we number our carbons like so, we can see that these are in fact different molecules, because here the double bond falls between carbons 1 and 2, but here the double bond is between carbons 2 and 3. So one of the distinctions we need to make with alkene molecules is that the actual location of where the carbon-to-carbon double bond is needs to be specified in the name, because as we can see with these 2 isomeric molecules, the double bond is not always in the same location in every form of the molecule. So instead of giving them carbon numbers, like calling this but12-ene or something like that, instead we can designate what position the double bond is in. So in butene, there are 3 different positions where this double bond can be. Position 1 is between carbon 1 and 2, position 2 is between carbons 2 and 3, and position 3 would be here between carbons 3 and 4. So here, we would call this molecule but1-ene to indicate that the double bond is here, whereas we would call this isomer but2-ene to indicate that the double bond is in a different position. Now, one final note on the use of the terms saturated and unsaturated. Now, if we compare the chemical formula, the actual number of carbons and hydrogens of but1-ene, which is the molecule that we have here, we have 4 carbons, and if we count hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 hydrogens here. If we compare that chemical formula to cyclobutene, which is the ring structure formula here, we can see there are 4 carbons and 2, 4, 6, 8 hydrogens in this ring structure as well. And so we can see that an alkene that contains 1 double bond is actually an isomer with the ring structure that has a single ring like this. So we can see, even though this cycloalkane here is technically still an alkane because it only has single bonds, we can see that they are also unsaturated because it is actually a structural isomer with but1-ene that we see here. So the conclusion that we can say is that every time we have a ring structure or every time we have a carbon-to-carbon double bond, this is what we call a single unit of unsaturation, meaning this is a single point at which we need to remove 2 hydrogens from the maximum number of hydrogens from the saturated form in order to create that unit of unsaturation. So for example, if we were to put 2 double bonds within a structure, such as this structure here, we would need to have 2 fewer hydrogens at this location, because if we count hydrogens, we can only have 2 on this carbon with the double bond as opposed to 3 in the alkane, and only 1 here, and likewise on these 2 carbons as well. So the result of putting in 2 double bonds is losing 2 hydrogens from what the alkane would look like over here with the first double bond, and another 2 at the second location here with the second double bond. Before the next video, where we actually discuss the nuances of naming alkenes in more detail, see if you can identify the 6 different structural isomers that you can actually draw using the chemical formula C4H8, and note that you have actually already been given 3 of them.